We live in a world that runs on code. From the planes in the sky to the cars on the road, incredibly complex systems are making decisions every millisecond. But how do we know they're safe? How can we be 100% sure they will always do the right thing? Well, today we're going to dig into something called Computational Tree Logic, a really clever language designed to answer exactly that question.
Okay, just think about this for a second. A self-driving car is dealing with a practically infinite number of what-ifs. A sensor could glitch, another driver could do something totally unexpected, the weather could change in a heartbeat. You just can't test for every single possibility, it's impossible. So the real question is, how do you go beyond just testing and start proving that no matter which future happens, that car is going to make the safe call?
So here's how we're going to break it down. We'll start with what this whole verification problem is really about. Then, we'll look at the special kind of language that was invented just to talk about time. After that, we hit a really crucial fork in the road, the idea of one future versus many. That's going to lead us right into the CTL toolkit, and we'll finish up by seeing how it can check every single possible path, all on its own.
All right, first up, the verification problem itself. We are surrounded by what you could call reactive systems, things that have to constantly make the perfect choice in a world where anything can happen.
Here's the problem in a nutshell. Testing by hand just doesn't cut it anymore. For any system that's even a little bit complex, the number of things that could happen is just astronomical. So you need something more powerful. You need a formal method, a way to use math to make absolute, ironclad statements about how a system will behave without having to run a single test in the real world.
So how did computer scientists even begin to tackle this? They figured out pretty quickly that they needed a whole new kind of language, one specifically designed to describe behavior over time, and that's how temporal logic was born.
The whole thing really kicked off back in 1977. A computer scientist named Amir Puneli came up with a way to reason about a single chain of events in a program. But then, just 5 years later, came this huge leap. In 1982, Edmund Clark and E. Allen Emerson asked a groundbreaking question. What if time isn't just a single straight line? What if it's more like a branching tree of possibilities? And that idea, right there, set the stage for everything that followed.
So Puneli's original idea is what we now call Linear Temporal Logic, or LTL. The easiest way to think about it is to imagine time as a single straight road. With LTL, you can say things like, eventually on this road, we'll pass a gas station, or every time we see a green light, we will eventually see a red one. It's super useful, but it has one big limitation. It only ever thinks about one road, one possible future, at a time.
And that brings us to the real fork in the road, because in the real world, systems face choices and random events all the time. So is time really a single straight line? Is there just one future, or are there many?
This, right here, is the conceptual leap that changes everything. Instead of that one straight road, what if we imagined a system's behavior as a massive, sprawling tree? Every single branch is a different choice, a different sensor reading, a different path the future could take, starting right now. And this really lays out the difference perfectly. LTL, on the left, that's our single road. But CTL, Computational Tree Logic, on the right, that lets us talk about the entire tree of roads. It lets us ask much smarter questions. We can finally distinguish between what might happen down one of those roads versus what must happen, no matter which road you take. Okay, so how does CTL actually do this? Well, it gives us a nifty little toolkit for asking really precise questions about this tree of futures. And it all starts with two big ideas called path quantifiers.
First up, we've got A, and that stands for all paths. You can think of this as the inevitability tool. When you use A, you're asking the strongest possible question. Is this property true no matter what happens down every single possible branch of the future? And its partner is E, for there exists a path. This is the possibility tool. It asks a much different question. Is there at least one path, just one possible future out of all of them where this thing happens? Now, you take those two tools, A and E, and you combine them with operators that talk about when something happens. So you have G for globally, meaning always. F for finally, meaning eventually. X for the very next moment. And U for until. And here's where the magic really happens. You put these little pieces together and you can make incredibly powerful statements. Take that first one, AG, not critical error. You've got A for all paths and G for globally. So this says, for all possible futures, it will always be true that there is no critical error. That's a rock-solid safety guarantee. Now compare that to the second one, EF, system reboot. E for exists, F for finally. This says there exists at least one possible future where the system eventually reboots. See the difference? One is an ironclad promise, the other is just checking if something is even possible.
So, we have this amazing expressive language. But so what? How do we actually use it? Well, this is where the real power of something called model checking comes in. The real genius of CTL is that it's built for computers. You can give a computer a model of your system, like a blueprint of all its possible states and moves, and a CTL formula. Then, the computer can automatically crawl through every single branch of that future tree and come back with a simple yes or no. Yep, your rule is always true, or nope, I found a future where it fails. This whole process, pioneered by these guys, is called model checking. It automated the act of proving something is safe, and that changed everything.
And believe me, this is not just some theory stuck in a lab. CTL and model checking are used all the time in the real world. They're used to verify the computer chips in your devices before they're ever made, to double-check the flight control software in airplanes, and to make sure self-driving cars behave safely. It's a fundamental part of how we make modern technology reliable.
So at the end of the day, that's what this is all about. Computational tree logic is the tool that lets us go from just hoping a system is safe to mathematically proving it. By looking at time as a branching tree, it gives us the power to explore every single possible future at once and to get real, concrete answers about the safety of the technology we depend on every day. But that leaves us with one big looming question. CTL works beautifully for systems where we can actually draw out that tree of possibilities. But what about the new wave of AI systems, the ones that are more creative, more unpredictable, maybe even a little chaotic? Their tree of futures might be practically infinite. So can we still use these ideas to guarantee they're safe, or are we going to need a whole new kind of logic for this new kind of intelligence? That is the next big challenge.